You have two-dimensional space, and in the space you are creating some curves. So I've seen previously how to create curves. So I've seen two types of curve. We have seen the cubic curve, and we have seen the Bezier or the quadratic curve. So for cubic curve, so you can see that here we have 2 points, and then we have 1 control point, and the cubic curve will be a curve like this. So the cubic curve will pass through this point, and here it will be close to this control point. So you have P1, here you have P2, and this is the control point. So this is called the cubic or the quadratic. We've seen also the cubic curve. So in cubic curve here, what does mean cubic curve? So here you have 2 points, and you have 2 control points. So as an example, you have seen the curve like this. So here we have P1, P2, and you have control point 1, and you have another control point 2, and the curve will pass through these 3 points, P1 and P2. And here we will have here an approximation for the control point 1 and the control point 2. So the curve will be something similar to this one. So it should pass here through these 2 points, P1 and P2, and here we have an approximation for the control point 1 and control point 2. So quadratic curve, that means here it is a curve with the polynomial order equals to 2. So here the order is 2. Okay, and here for the cubic curve, here the order is 3. It's cubic curve. And here quadratic, that means we will have an order that is equals to 2. Okay, so for the curve in 3-dimensional space or in plane, it should be defined as a finite set of points and control points. So you can see that in this curve, we have some points and you have some control points. You have 2 points and 1 control point. Here you have the start and the ending point, and you have 2 control points for the cubic. Now, the following property should hold to make the curve more suitable for modeling. So in modeling general, we have to verify these 3 properties from the curve. So the first property is the controllability property. So let's see the details. So what does it mean, the controllability? So here we are talking about the properties to have a good curve in modeling. Okay, so here we have the property that we have to, or the property that the curve has to feel, okay, to be a good curve in modeling. So the first property here is the controllability. What does it mean, controllability? It is the influence of the parameters of the shape of the curve. So here the influence can be understood in an intuitive way. Yani if you make any change on the parameter of the curve, so directly you know what is the result of this change. For example, here, let's suppose that we have cubic curve. P1, P2, 1 control point here, so the curve would be like this, for example. Now, if you change P1, if you make P1 here, so you know in an intuitive way that the curve will be here, like this. If you change P2, for example, in this location, you know approximately that the curve will be looking like this. So here we have the controllability. So you can control the curve. Okay, so when the shape of the curve has to be changed, it should be clear for the user which parameter should be modified. So this is for the controllability. Now the second property is the locality principle. So what does mean the locality principle? So it must be possible to carry out local changes on the curve, and then modifying one control point should only change the curve in the neighborhood of this control point. That means here, if you have a curve like this is the control point. So we have 2 points and 1 control point. Okay. Now, if we change this control point, if we make it here, so you can see that this will not affect the whole curve, but the curve will be something like this. So you can see that modifying this control point will change only this area. So you are talking about the neighborhood of this control point. And I cannot change the control point from one place to another. and the whole curve will change dramatically. Okay. So if you change the control point, only this area will change. And if I change the control point, I cannot have a curve like this by just changing the control point from this direction to, or from this position to this position. Okay. So when you change the control point, this will not alter the curve completely. Okay, so this is the locative principle. If you change the control point, so this will affect the area that is near to this control point, the neighborhood of this control point. Now, the third property of the curve, or the third property that the curve has to feel, is the smoothness. So here we have to make the curve as smooth as possible. So what this means, smooth curve? For example, let's suppose that we have this curve. So you can see that the curve here is not smooth. So you can see that here it is sharp and it is sharp also here. Okay, so we have to have generally the curves. So if you want to make one curve, generally we are talking about smooth curve. Don't have the sharp edges. So you have to avoid using the sharp edges. So here the curve should satisfy certain smoothness properties. So it should not only be continuous without jump. So here, first of all, the curve should be continuous without jump. It should have also no sharp bends. You have to avoid using sharp bends. You have to make one curve. It's just one curve. Don't make it, for example, a curve. One part like this, another part like this. So it is one curve. It should be here continuous, first of all, and it should be also smooth. So here we are talking about two different curves. So you want to make a shape like this here, you need one curve here and another curve. If you want to make just one curve, so in one curve, it should be as smooth as possible. So the later property requires the curve to be differentiable. So here we are talking about the mark property. So how we can know if the curve is smooth or not. So if the curve has a derivative, so it is smooth. If the curve doesn't have a derivative in all the points of the curve, that means here the curve is not smooth. Any question about this? So these are the properties that the curve has to follow. Okay, we have here now for the type of the curves, we have two types of curves. Okay, let's suppose that I made an experiment and for example, are measuring the temperature here. We are boiling water, for example, and we are measuring the temperature over the pipe. And then we have a point, measure at some point, and we have curve like this. Okay, or we measure at 5 points and we have this measurement. Okay, now how we can make this curve? So here we need a curve. Okay, so we have two options here to make a curve. We can make interpolation or we can make approximation. Interpolation means the curve that passes through all the control points. So if you want to make interpolation, that means here the curve should pass through all the control points. This is an example of curve in which you are making interpolation. You can see that the curve passes through all these points. Okay. Now the second way is to make not interpolation but approximation. So what does it mean, approximation here? So only requires that the curve get close to the control point. So you can make a curve like this. So you know that the temperature will be something near to the linear curve. So you can make a linear curve like this. So you can see that this curve here is close to the control points. So as close, we can make a curve as close as possible to the control points. Okay, so we see here two types of curve: the interpolation and the approximation. Now, which one is better? What do you think?
Interpolation, because it passes all the control points.
So when you make a curve that passes through all the control points, sometimes it makes irregular points. Okay, sometimes you have some errors. So I have a point here, but we have to ignore it. Okay, so we can make the curve as close as possible to the control point, which is the better, it's the best option. Okay, so here, especially in modeling, it's better to use approximation. Okay, so you can see that in quadratic curve, the control point here, and the curve will be like this. In cubic, if we take two control points, one here, one here, so you can see that the curve will be something like this, for example. Okay, so here we will not pass through all the points, so we'll start from P1 to P2, but we'll try to be close to this control point and to this control point. Okay, so in modeling here, it's better to use approximation. Now, with interpolation, we can face some problem. Okay, because here generally to make interpolation, if you have points, so we can have a curve, for example, like this. So this is a curve, and this curve passes through all the control points. You can have here, suppose that we have the same point, and we can have a curve like this. So this is another curve that passes through all the control points. Okay, so here, if you are making interpolation, here we are using mathematical polynomial. So here it depends on the order of the polynomial. Okay, so if you create a polynomial with high order, you can have an output like this. So you can see that this curve, it passes through all the points. But we don't need a curve like this. We prefer a curve like this, for example. Okay, so this is the problem of the interpolation. So it is an overfitting. Okay, now the interpolating. So here we have rejecting interpolating polynomial. Now we'll see what are the problems of the interpolation. Interpolation, yani you have to go or we have to pass through all the points. And to do this, we have to use here polynomials. And when we say polynomials, so it can be order 2, order 3, 4, 5, order n in general. Okay, so to make an interpolation, you have to use the polynomial. So the interpolation with polynomial is not suited for the modeling purposes. Why? So the evaluation of the polynomial of higher degree leads to high computational cost. So first of all, you have, for example, polynomial with high degree, for example, 10, 15. So here we have a computation cost. So this will make your program consuming a lot of power from the microprocessor. Okay, so it will be complex problem. You are increasing the complexity of the program. And if you increase the complexity, here you need more processing time. Okay, and also the interpolation. So the interpolation polynomial doesn't satisfy the locality principle. That means if you modify just one point, this can change all the coefficient of the polynomial. So what does it mean polynomial? So for example, let's suppose we are using x. Okay, so we can have, for example, here a0 multiplied by x to the power of 0 plus a1 multiplied by x to the power of 1 plus a2 multiplied by x to the power of 2. So here we have an example of polynomial with order 2. Okay, we can have polynomial with order 3. So we can add here plus, for example, a3 multiplied by x to the power of 3. Okay, so here the highest order is the order of the polynomial. Okay. So the polynomial of higher degree can oscillate between the control points. So you can have, as I explained, curves like this. Okay, and if you make a polynomial with higher order, you can have, for example, a curve like this. This is the curve, and this is the curve passed through all the point. Okay, but we don't need a curve like this. So these are the problem of the polynomials. The same thing here, or the same example, you can say that the curve here is oscillating. Okay. So it's smooth curve, but here the curve is oscillating. So we need the curve to pass through this point. Okay, in this point, for example, so instead of having linear curve, so we can have a curve like this. So this is an example of polynomial with degree 5. So the equation of this curve will be something multiplied by x to the power of 0 plus something a1 multiplied by x to the power of 1 plus etc. Then we have a5 multiplied by x to the power of 5. So this is x of t. Suppose that the axis here is t. Okay. So we can have f of x equals, and then we have the now let's see another alternative. So here let's see the Bernstein polynomial or Bernstein polynomials. So for the Bernstein polynomial of degree n, they are a class of polynomial with better properties than interpolation polynomial. And instead of using polynomial, we use now, instead of interpolation, we use approximation. And the Bernstein polynomial rings are the polynomial that you are using for the cubic curve and for the quadratic curve. So in Java, we are using cubic curve and we are using quadratic curve. And these two types of curve, they are special type of Bernstein polynomial. This is the Bernstein equation. Okay. So the ith Bernstein polynomial of degree n is given by this equation. So why do we need this equation? So this equation is used to calculate here the curve or the equation of the curve. So let's start with this formula and then we return back to the previous slide. So for the Bernstein curve here, we are talking about the Bezier curve. So the curves that we have seen previously, the quadratic, cubic curve. So all these curves, they are called Bezier curve. So here we have a Bezier curve with order 2. And here we have a Bezier curve with order equals to 3. Okay. Now, what is the general formula of the Bezier curve? Okay, so this is the general formula. From this general formula, we can have the formula of the quadratic curve. We can have also the formula of the cubic curve. So we'll see here, or just to change this n by the order, okay, we will get the formula of the curve, okay, or the parametric equation of the curve. So here, the curve is defined as x of t. So here we have the time axis, okay, equals to what? Equals summation for I equals to 0 to n of bi multiplied by here bin of t. So bin of t is the Bernstein parameter. Okay, so what does it mean? So bin of t is this one. So bin of t. So how to calculate it? So here we have n choose I. So here we can use the combination in statistics. You know the NCR. Okay, or CR like this. So this is the combination. Okay, so we say that you have here n choose R. So we can use this notation, or we can use this notation, or this notation, or NCR like this. So we have many notation for the combination. Okay, so how to calculate bin? So here it is n choose I multiplied by 1 minus t to the power of n minus I multiplied by t to the power of I. Now, what do you have to know? We have to know how to calculate b of I, so or bi of n. So here we have to know how to calculate it. So generally, we start from this formula. You have to know this formula. So it is very simple. So what do we have here? X of p equals summation of bi multiplied by bn or bin of t. So what does this mean? So let's suppose that we want to create the formula of Bezier curve with order 2. So order 2 yani quadratic curve. So quadratic means n equals to 2. So what is the formula of this curve? So how this curve is defined? So here we have x of t equals to what? It is summation for I equals 0 to n of bi multiplied by bin. And bi here, these bi are the control points. So these are the points of the curve. So generally here, if you have a quadratic curve, how many points do you have? The total number of points. You need 3 points. So these 3 points are B0, B1, and B2. So these are B0, B1, and B2. So these are the different PIC. The I means if I equals to 0, we have B0. If I equals to 1, we have B1. If I equals to 2, we have B2. Okay, so now what is x of t? So it is summation of the I multiplied by b I n. So initially we have I equals to 0, so we have B0 multiplied by Bernstein 0, 2. So here our n is 2. So this is the first term. Plus, now I will be incremented. So here we have n equals to 2. Then I will be incremented to B1. So here we have to make B1 multiplied by Bernstein 1, 2. Plus the last value I will be 2. So here we have B2 multiplied by the Bernstein 2, 2. So these B0 are the point of the curve, are the control point that we have to make the curve. Okay, and here B02 of t, B12 of t, and B22 of t. How to calculate these Bernstein term? We have to use just this formula. You have to know, you have to memorize this formula. Because if you memorize this, you can create the curve of every, or you can calculate the equation of every curve. Okay, so here we can have the equation of the curve with order n equals to 2, or n equals to 3, or n equals to 4. You can see that it is very easy to find the curve, or the parametric curve, or the parametric equation of the curve. Okay, now let's calculate. So what do you have here? We have B02, B12, and B22. Now, so I have to calculate B02 t, I have to calculate B12 t, and you have to calculate B22 t. Now let's do it together. Let's calculate now B02 of t. So this B02 of t. So here it is 2 choose 0. So let's use here 2, 0 multiplied by 1 minus t to the power of n minus I. So here our I is 0. Because here you have 0, so I is 0, and n is 2. So 2 minus 0, so it is 2. Multiplied by t to the power of I, and our I is 0, so it is t to the power of 0. So here what is 2 choose 0? So here we are using here the properties of the mathematical properties that we have seen in previous courses. So here we have 1. So here 2 choose 0 is 1. And it's here 1 minus t to the power of 2. So it is 1 minus t to the power of 2. And t to the power of 0 is 1. And here B0 to t equals to what? Equals to 1 minus t squared. This is the first Bernstein elements. Okay. Now I have to do this with B12 of t and B22 of t. So let's calculate B12 of t. So same thing here. We have 2 choose 1, and we have to make 1 minus t to the power of 2 minus 1, and multiplied by t to the power of 1. Okay, so here 2 choose 1, so the value here is 2. So we can check this. So here, you can search. You can use the calculator or here on the net. So you can see that here we have the NCR calculator or combination calculator. So the value of n in this example equals to 2, and we want to calculate now C and R, and our R is 1 and our N is 2. So to calculate, you can see that the value here is 2. Now we have to continue. So here we have 2 t to the power of 1 equals t, and here we have 1 minus t to the power of 2 minus 1, and to the power of 1. So you 2 multiplied by t to the power of 1 minus t. So this is the b 1. And then we have to calculate the b to 2. So this is here, b to 2 of t equals to what? You have 2 choose 2, which is equal to 1, multiplied here by 1 minus t to the power of 2 minus 2 to the power of 0, multiplied by t to the power of I, so t to the power of 2. So here, this is 1, here we have 1, so we have here just t squared. Now we have b0, 2 of t, we have b1, 2 of t, and we have b2, 2 of t. Now we can extract the formula, so here x of t will be what? Will be b0, the first control point, multiplied by b0, 2 of t, which is 1 minus t squared. Change this one. Plus 1 multiplied by 1 by what? By b1, 2 of t, which is 2 t, 1 minus t. Plus the next control point, which is b2, multiplied by what? But b2, 2 of t, which is t squared. This is the formula of the quadratic curve. And in Java are just using here the quadratic curve. But how Java is making this curve? So Java is using this formula to create the quadratic curve. So this is how to find the formula of the quadratic curve. So if you need the cubic curve, so same thing. We return back to the formula here. Okay, so here for the quadratic, for the cubic curve, we just to make n equals to 3. So let's discard everything here. Now, if you need the formula of the quadratic curve, so how we do it? So here our n will be 3. Okay, so x of t will be summation for I equals 0 to 3 of bi multiplied by bin of t. So x of t equals to what? Equals to b0 multiplied by b0, 3 of t plus b1 multiplied by b1, 3 of t plus, if you have cubic curve, we need 4 points. Okay, so let's return back to this example. So we can see that we have 1 point, 1 point, 1 point, and another point. We need 4 control points. The control points are here the different bi. b0, then b1, then b2, multiplied by, then we have the third control point, which is b2. So here we have b2 multiplied by b2, 3 of t, plus b3 multiplied by b3, 3 of t. Now, these b0 are the different control points. We have just to calculate what? We have to calculate b0, 3 t. We have to calculate b1, 3 t. We have to calculate b2, 3 t. And we have to calculate b3, 3 of t. So how can we make this calculation? By using this formula. So let's try to make b0, 3 of t. So what is b0, 3 of t? Now just here to make I equals to 0 and n equals to 3. So b0, 3 t equals what? Equals equal to 3, choose 0 multiplied by 1 minus t to the power of n minus I. So we need 3 minus 0 multiplied by t to the power of I and t to the power of 0. Okay. Now the value here is 1 multiplied by 1 minus t to the power of 3 multiplied by t to the power of 0, which is 1. So here it is 1 minus t to the power of 3. So here we have just to change this by, so here x of t will be b0 multiplied by 1 minus t to the power of 3. This is the first item, plus b1 multiplied by this element, you have to calculate this element, etc. So this is very, very important. So you have to know how to calculate the parametric equation of the curve with n equals to 2, with n equals to 3, and let's say with n equals to 4. And you have to practice at least these 3 values for the polynomial. Any question on this? So here you can see that it is very easy to find the equation of the Bernstein polynomial. Now, properties of the Bezier curve. So the Bezier curve interpolate the first and the last point. So in the Bezier curve, you can see that you are interpolating the first point and the last point. And for the control point that you have here, so here we are not making interpolation, but we are making approximation. And the curve passed through this point and this point. So here we are making what? We are making interpolation. For this point and this point, we are making interpolation. And for this control point, we are making approximation. Okay, so here the Bezier curve will interpolate the first and the last point. And x of 0 would be the same as the curve. So the first point here will be b0. And x of n will be bn. And the last point also will be interpolated. And we'll use the same points. Okay, and then we have to interpolate the different other points. So in general, the curve doesn't pass through the other control points. So you can see that here for the Bezier curve, for the quadratic curve, we have just one control point, and the curve doesn't pass through this control point, pass through the first and the last points. Same thing if you have a cubic curve. So the curve passes through the first and the last point. And for the 2 control points, so here we are making approximation, or we are moving the approximation and not interpolation. Yani we will interpolate just for the first and the last point, and then we have to calculate here or interpolate the different control point, and the curve doesn't pass through the other control points. So the Bezier curves are also symmetric with respect to their control point. Yani the control point B0 to Pn, and from the n to B0, then they will give the same. Now, let's see special type of Bezier curve. So here the special type of the Bezier curve is the curve with n equals to 2, and this will give us the quadratic. Okay, so for the purpose of computer graphics, only the cases of the plane. So plane yani are in 2D, so here we are using n equals to 2. Okay, and the 3-dimensional with the space, so space here we have p equals to 3, that means we are in the space, and the polynomial will be n equals to 3. So the order here will be. So in Java, we have seen in the previous classes that cubic curve means n equals to 2, or quadratic curve means n equals to 2, and cubic curves and n equals to 2. So these are the special cases that you have seen. So the degrees are 2 or 3. Now, what is the parametric equation? So the parametric equation describing the above 2 curves can be derived from the main Bezier equation. Okay, so here we'll have the equation of what? The equation of the Bezier. So you can see here that you have 2 points, or 3 points, or P0, P1, and P2. So these are the points. And this term here is B0, 2, T, and this term here is the 1, 2, P, and this term here is the B, 2, P of T. And we know how to calculate these Bernstein values, so we know how to generate this one. And if you know the general formula, no need to memorize this. So directly you can extract this formula from the general formula here and the Bernstein polynomial. So these are the main things that you have to understand in this lecture. Any question about this? So try at home to generate the parametric equation for n equals to 2, for n equals to 3, and for n equals to 2. Okay, so generally in all the final exam, we have a question related with the Bernstein parametric curve. Okay. Now the problem here with Bezier curve. So let's suppose that we have a curve like this. Okay, so how many points do you have here? 1, 2, 3, 4, 5, 6 points. So with 6 points, we can have a Bezier curve with n equals to 5. Because here the number of points is the order plus 1. So if you have here n equals to 2, how many control points or how many points do we have? We have 3 points. B0, B1, and B2. Okay, now if you have 1, 2, 3, 4, 5, 6 points, so 6 points means we have B0, B1, B2, B3, B4, and B5. And then here the order here will be order 5. Now to calculate a Bezier curve with order equals to 5, so it is more complicated task. So if you have 5 points, it's okay, but if you have 20 points, if you want to make a curve, and here you have 20 points. In that case, the calculation of the Bezier equation will be very, very complex. Okay, so failure of the Bezier curve. So despite the nice property of the Bezier curve, they are not suited for a larger set of points. So here, because the number of points is n plus 1. So if you have 20 points, that means the order will be magnitude. So what is the solution here? So the solution will use Bezier curve, but we use Bezier curve for a number of points that is small number of points. Okay, so it is like here pi or piecewise Bezier curve. That means if you have a curve like this. Okay, so instead of making here Bezier curve with order 1, 2, 3, 4, 5, 6, 7, 8 with order 7, we can create a Bezier curve for the first part. And we can create here from here 1, 2, 3, 4. We can create a Bezier curve for this part. And then I can join the two parts together. Okay, so this is one of the techniques that we can use. But if you did this, if you do this, you can see that here we don't have the smooth area. So you can see that here we have sharp area because we have a connection here of two curves. This is the first curve, and here we have the second curve. So we don't have something that is smooth like this. So here there is a problem. Okay, so we will see how to correct these problems. Okay, now the idea is that instead of using one Bezier curve, we use many Bezier curves. Okay, so we can have like this. Let's suppose that we have this point. We can make a Bezier curve with the first 3 points. Okay, then we can make another Bezier curve with the next. Now, we took already the first point. Now the second curve, we start from the second curve, from the second point here. Now we can make the second Bezier curve here. And the third Bezier curve will be starting from this point. So now we move these 3 points, make another Bezier curve. Then we can move the next 3 points to make another Bezier curve. And then here we can join the different Bezier curve together. So this is what does mean B spline. Okay, so instead of using one Bezier curve, the B spline is preferred to define approximating curves for a given set of control. Do not make one Bezier curve, but we make many Bezier curves. Okay. So the Bezier or the B spline, Bezier spline are composed of a number of Bezier curves of lower polynomial degree. So here, what is the advantage? So here, instead of using n equals to 7, okay, we use it just n equals to 2. So I'm using polynomial with lower degree. But instead of having one curve, we can have here many curves. Okay. For a sequence of n control point, for example, we take n equals to 4, a Bezier curve is computed, and the last control point of the sequence is used as the starting point of the next sequence. So you see this example. So here you have 1, 2, 3, 4, you have 7 points. So instead of making just one curve, we can make here, we can divide this into two curves. So this is the first curve. So you can see that here we are using cubic Bezier curve. So we start from P1 to P4 by using these two control points. So we use here interpolation for P1 and P4, and use the approximation for P2 and P3. And then we can make another curve here from P4 to P7. And here we have two control points, we have P5 and P6, they are control points. And the curve starts from P4 to P7. But in order to be able to have a smooth curve, you can see that the P3, the P4, and P5 should be on the same line. So here, this is the tangent of the curve. So the tangent of the curve in the point P4 is this line, which is the line having the point P3, P4, and P5. So to solve the problem, so if you don't have this, the curve will be like this. So the first part will be like this. The second part can be, for example, like this. Like this. So you can see that here, what we have here edges. Okay. So the connection between the 2 points here. So the connection between the two curves. If you don't have the 3 control points are collinear and in the same line, you will have here edges. For example, one line like this, another line like this. Okay, so here we have points. I'm accentuating the. So in order to avoid the sharp bends, so here we are talking about sharp bends. Okay, between at the junction between the Bezier curves. So the junction meaning the connection between or the intersection of the Bezier curves. So the junction here they are called nodes. So each node and its two neighbor inner Bezier points should be collinear. So this is called a node, which is the connection of the joint between two Bezier curves. And here we have one inner control point, here we have another inner control point. So these 3 points, they should be in the same line. That's why you see in the next problem or in the next program, you can see that starting from the point P1, P2, P3, you have to calculate the different inner Bezier points. And in the problem that we're calling them B0, B1, B2, etc. Starting from what? Starting from the different point P1, P2, P3. Okay, so initially we have the different points. And then we have to calculate the control point that we asked. So the idea here, so you can see that here we want to make a beast line. So you can see that from the different point P1, P2, P3, we can extract here the different. So here we are making what? We are making the approximation of B0, B1, B2, P3, and P4. So you can see that here B2 equals P2 plus P1 divided by 2. So if we say P, yani for every point P1, so it has the X component, X1 for example, and Y, Y. For the point P2, it has the X and Y, so here we can have X2, we have Y2. So how to calculate B2? To calculate B2, we have to find what? We have to calculate, for example, the X component, and we have to calculate the Y component. So how to calculate the X component? By using this formula, which is the X component of P1 plus the X component of P2 divided by 2. So now for this X here, it will be X1 plus X2 divided by 2. And how to calculate this Y? We have to use the same formula. So the Y will be Y1 plus Y2 divided by 2. So this is for calculating B2. Calculate B3, so you can see that we have to make 2P1 plus P3 divided by 2. So we have to apply this for the X component and we have to apply this for the Y component. So here we have the program. Okay, so this is the program that can check the program at home, but here the idea is we have many points from P0 to Pn. So how we can make this curve? So we can make the first curve here. So we can take now the first 4 points T0, T1, T2, T3. So this will make one curve. And then we can continue. Now the next curve will be T1, T2, and T3. The next curve. So here we can move this point. Okay, T1, T2, T3 can change. Now we can start from here, and we can start from here. We can start from here till the end. So here, instead of making one curve with high order, we can make many curves with lower order. So then we an order of 2 or an order of 3 to create a curve with any order, with any number of things. Any question about this? So here we have the code, okay, and we have here an example of generating the shape of heart by using the general path. So here we are using abstract method that we can have. So you are using the shape interface. In the shape interface, it has 10 abstract methods. So the methods that we can use here, we can use the contain method, the intersect method, the get bound, the get bound 2D method. So these are the methods that we can use for the shape interface. Okay. So this is the shape interface of many abstract. Okay. So we can use a rectangle, can use points, can use point to deal, can use double X, double Y. So we can use the get bound method, get bound 2 method. So here, this is the contain method. So these are some methods that we can use for the shape interface. And we are using these methods to this program. So here you can see that are leading to the public class art, and it implements the shape, the face. Okay. This is the program, and this is the results. So this is an example of generating the curve. Okay, and how we can generate this curve by making many, or by making, or by cascading here many basically. Lower. For the next class, inshallah, will be the last.